Imagine you're an astronaut embarking on a journey into space. The nice sunny day in Florida or wherever you're launching from, blue skies everywhere. You get into your rocket, it blasts off, and as you climb higher and higher into the sky, you notice it's getting darker and darker, even though you're getting closer to the sun. How does that make any sense? Well, the answer is you can only see light that you're looking at directly, or if it's been refracted or bent through something, or reflected off something. You can't see it from the side. And I'll prove this to you with a little experiment. I'm out in the back garden, it's nighttime, it's completely dark. I have a GoPro camera strapped on top of a torch. The torch is actually on, but you can't see any light until I bring a burning piece of paper close to the beam of light. Smoke particles blow into where the beam of light is coming from the torch, and only then can you see where the light is. You can only see light if it's been reflected off something or been refracted or bent through it. If you're an astronaut on a spacewalk or looking out the window of the International Space Station, you can see the sun as a bright white star. But either side of it, it's pitch black. There's no other light sources apart from the sun. It's only when you're in an atmosphere, which has very fine particles floating in it, that the entire sky is going to be bright, so that the sunlight can be scattered and reflected and refracted off different things. If you're an astronaut walking on the moon, you will see the sun as a bright white star. You won't see any scattered light, you won't see any blue skies. In fact, you'll see stars as well right next to the sun. Now, these don't show up too well in photographs, but an astronaut standing on the moon can see the sun and then stars either side of it. Okay, that explains why the sky is bright during the daytime here on Earth, but not on the moon. But why blue? When you pass white light through a prism, it'll split into its different colours, the colours of the rainbow. Or if you pass light through a raindrop, it will give you a rainbow. And it's always these colours: red, orange, yellow, green, blue, indigo, violet. Or Roy G. Biv is an easy way to remember it. ROYGBIV. Now, our eyes are very good at seeing all these colours up until about indigo. We don't really see all of indigo or violet. And that's just the way that our eyes have evolved, so we don't see violet very well. Now, if you imagine the prism is sitting on the ground, if you look at the red beam of light at the very top, it's bent down a little bit towards the ground. Whereas if you look at the violet beam at the bottom, it's bent down much more, as are the indigo and the blue. Now, the reason for this is that the lights are different wavelengths. So red light has a long wavelength, and violet light or blue light has a short wavelength. Now, what's wavelength? So wavelength is the distance between the two peaks of a wave. Whether that's a wave of light or a wave of sound, it's the same thing. It's easiest to explain with sound. So the shorter the wavelength, or the closer the waves are together, the higher the note will be. The further apart they are, the lower the note will be. And it's the same with light. Red light has a long wavelength, blue light has a short wavelength. So different objects will resonate or give a sound or a light pattern that is related to their size. So big objects like a cello will give a very low note, whereas a violin, which is smaller, will give you higher notes. The notes that you get from a ukulele are shorter wavelength and higher notes than you get from a guitar. Just like when I hit these glasses, the bigger glass gives a lower note, longer wavelength. The smaller glass gives a higher note, shorter wavelength. And the smaller the glass, the higher the note and the shorter the wavelength we would get. And it's the same with particles. The smaller the particle, the shorter the wavelength that it will reflect. So which particles are going to remain high up in the atmosphere and are going to be there to reflect sunlight? The heavy particles or the really small particles that are really light? It's going to be the smaller ones. And which wavelength are they going to reflect? The shorter wavelengths. The wavelengths of blue light. Now, if we remember back to the prism, It's actually violet is the shortest wavelength, and that's the one that will be scattered best. So the sky is actually violet in colour, but we can't see violet. The last colour that we can see is blue. So the sky is actually violet, but to our human eyes, the sky looks blue. But the sky doesn't always look blue. Sometimes it looks really pink or even red at sunrise and at sunset. Why does this happen? So red light likes to go on in a fairly straight line. It doesn't like to be scattered around. Whereas blue light and violet light bends down quite a lot and likes to be scattered around. It scatters very, very easily. Now in this drawing, it's 12 noon and you're staring straight up at the sun in the middle of the day and a lovely blue sky. As the sun's white light hits particles in the upper atmosphere and the blue light is scattered by the fine particles, giving lovely scattered blue light all over the sky. And the sun looks bright white or even a tiny bit yellow. But at the end of the day, when the sun is going down and about to go below the horizon, the sun looks really red and the sky looks really red. Why does that happen? So we'll draw the sun again, this time we give him a nice smiley face, and we'll look at a beam of light that's travelling towards somebody looking at a sunset, not somebody looking straight up at the sun in the middle of the day. This time the beam of light is passing through lots of atmosphere because it's at a shallower angle, which means it's going to hit lots and lots more fine particles in the upper atmosphere, which means lots more of the blue light is going to get scattered. And very, very little blue light reaches the person standing looking at the sunset. Only the red light gets to them. So the sun looks red, the sky looks red, everything looks red. But the sky still looks blue to the person on the other side of the earth looking up at the midday sun. Remember when I said if you were on the moon you'd never see a blue sky? Well, it's happened once and it's been photographed. And it was created by an astronaut called Alan Bean. As the astronauts were walking around on the moon, they had backpacks to keep them oxygen and water and to keep them cool. And one of the things the backpacks did was to allow water to evaporate off to keep the astronauts cool. Now, on the moon, in the vacuum, that water vapour instantly turned to incredibly small, very fine ice crystals. And in this photograph, the sunlight is catching through these very, very fine particles. And wouldn't you know it, what colour is the atmosphere that was created around Alan Bean? I hope you enjoyed that, and I hope you enjoy blue skies and red sunsets whenever you see them even more now.